All right, so this one says the Department of Tourism reported that in May of 2017, approximately 63% of tourists to the Philippines were from Asia. They also noted that it was the first time that the Philippines had more than 500,000 tourists in the month of May. Suppose another organization had taken a simple random sample of 600 tourists of that population. Assuming that the reported 63% claim is accurate, what is the approximate probability that the other organization's results were within 2 percentage points of the Department of Tourism's results? So what we're saying is that in reality, like in truth, 63% of tourists to the Philippines are from Asia. What we are going to do is imagine that we're taking like samples of 600 tourists. We won't always get the number 63%. It's going to be a bell curve, assuming the sample's big enough. 600 is definitely big enough. It's going to be a bell curve. The center of the bell curve will be whatever we expect to get. In this case, we're measuring a percentage. As a decimal, we can say it's 0.63, 63%. So we're going to use these green equations on the right. This is the mean of our sampling distribution. I'll do another arrow. It's P, like the mean of our sampling distribution. The standard deviation of our sampling distribution is going to help us answer this question because it's asking what's the probability of getting within 2 points. I don't know quite yet because I don't know what the standard deviation is. That can only be determined with this formula, and it's going to require the sample size. So our standard deviation, also called the standard error when we're thinking of sampling distributions, is the square root of P times 1 minus P over N. So for us, P is 0.63. So 1 minus P is 0.37. 0.37. And this is over the sample size of 600. So I'm going to hit this into a calculator. So it's going to be, bear with me, 0.63 times 0.37. I'm just going to hit that out. Don't want to make mistakes. So I'm going to divide this by 600. Okay, and I'm going to take the square root of that answer. Standard error is 0.019. I'll call it 0.02. Call it 0.02. Well, that actually works out pretty well. So let's think about why. So 0.02, what does that mean? Standard error is about, I'll use these little curvy ones, about 0.02. So what does that do in percentage terms? That's like 2%. What that does is it tells us that 68% of the time we take these samples of 600, we're going to get answers that are plus or minus 2%. So it's going to take us to 0.65 and down to 0.61. So if we take samples where N is 600, if we take 600 person samples, 68% of the time we should be getting results between 61 and 65%, assuming that 63% is true. So that is what these things are kind of saying, is like, what is the probability that your sample proportion is between 61 and 65? And we said that is exactly one standard deviation away. So I'm going to use 68% is the rule of thumb in the empirical rule. The number that's going to get us closest to for this is the C69. I know that's not exact. It is definitely the closest answer if 68 is the one that you're using, if you're using the empirical rule. You can use these scores and use a normal distribution table, and maybe we'll have to do that as we go through this. So we'll see. All right, so this question, multiple choice, has a few distributions, different shapes. The C is a normal distribution. B is skewed right. It's heavily weighted on the left. A is skewed left, so it's heavily weighted on the right. D is a uniform distribution. We don't have to talk too much about why that wouldn't happen. Let's talk about like what we would expect and what answer we'll choose. Okay, so this question says, according to a Gallup poll in 2006, old school, about 10% of Americans said they were very afraid of flying on an airplane. So 10% of Americans said they're very afraid of flying. Suppose we took a random sample where N equals 40 people of the population. So what we're doing, it says, which of the following distributions is the best approximation of the sampling distribution of the proportion of people who were very afraid of flying? So what would we hope would happen? We would hope that if the sample size is big enough, we would hope that it would actually look like C, I believe. So the samples would be this kind of normal distribution where the center would be wherever we think the center is, but it's balanced on both sides. It's unbiased. That is true as long as the sample size is big enough The 40, it seems big enough because it is over 30. There is one other condition that is typically used, and it's 10 successes and 10 failures. So we have to be able to expect, if we're asking people, are you very afraid of flying? We have to be able to expect at least 10 people to say yes and 10 people to say no in order to use this kind of normal sampling distribution. The problem is that if only 10% of people are going to say yes, and we only ask 40 people, how many people should say yes? Well, it's going to be 10% of 40. 40 times 0.1, that is 4. So the problem is this expectation, right? If we ask 40 people, we should only expect about 4 of them to be very afraid of flying. That is a problem for using the central limit theorem. So like the sample size is just not big enough because we cannot expect 10 of these successes. So we're not going to get enough successes. If we're measuring success, we're going to underreport. There's not going to be enough. So we're going to get too many numbers under 10%. So we're going to get too many numbers under 10%. Our distribution is going to be weighted under 10%. It's going to be heavy to the left of 10%. So that's why B is going to be our answer here. We have this hump. The majority of our distribution is actually under the number we're looking for versus A where it's over. So I like B on this one. You can read the descriptions there as well, and maybe that'll help as well. So this question says, a manager of a customer support center takes a simple random sample of 40 reported issues, finds that 22% of the sampled issues require more than one call to resolve. Let me see here. Okay. Let's see. So is the sample even, yeah, the sample is big enough. 22% of 40 it's actually, I think that's technically not big enough, but the answer choices are all assuming that the sample size is big enough. So let's just roll with it. The manager may take a simple random sample like this each month. Suppose that it is really an average of 25%. Oh, okay, that makes the sample size big enough of the approximately 1,000 issues reported per month that require more than one call. Let P hat represent the proportion of a sample of 40 reported issues that require more than one call to resolve. What are the mean and standard deviation of the sampling distribution? Wow, there's a lot going on here. Okay, we have to think about like what is the result of a single sample and what is the true actual number. It says here the manager of a customer support center takes a random sample of 40 and finds 22%. So this is just like one sample. That's just one result of many. Later it says suppose that it is really an average of 25. So what we're going to do, this is going to be the center of our sampling distribution because it is the true percentage. That's what we said in the light green here. The true percentage is the middle. So our sampling distribution will have a mean of 0.25. That rules out A and C already. A and C are gone because they're not using the correct center or mean of the sampling distribution. I am going to need to already erase this because I need to move this. So it's either B or D because B and D have the correct center of the distribution. The center needs to be at the true average of 0.25. Now the question is, I guess at this point, which of these has the correct standard deviation? There's this versus this. So if we look at our formula, the numerator is P times 1 minus P, and we have the same numerators. The denominator is different. The denominator should be the sample size. So are we taking samples of 40 or samples of 1,000? That's the only question. Samples of 40 or samples of 1,000, and it's samples of 40. Let P hat represent the proportion of a sample of 40 issues. So the sample size is 40. So that's why your answer here is going to be D. It's going to be D. It uses the correct sample size of 40 down there, and the correct mean as well, or average. This one says a car manufacturer crash tests a certain model of car and measures the impact force. The test and model in question produce impact forces that are normally distributed, that's cool, with a mean of 30 metric tons and a standard deviation of 1.5. So we're thinking of a population that is normally distributed with a mean of 30 and a standard deviation of 10. This would be 40, 20. This is for the whole population of cars. And I think what it's measuring is the impact, average impact force of 30 metric tons. So suppose that a manufacturer tests a random sample of 4 cars and calculates the sample mean impact force. What is the probability that the mean impact force from a sample of 4 exceeds 30.75? So a couple things here. There is the option in this to select E. What E would mean is that the sample the sampling distribution is not normal, that would mean the sample size isn't big enough or something like that. So the sample of 4, we would think that that's not big enough. It really doesn't meet a lot of our requirements. The key thing here, though, is that it's just kind of a product of where we're pulling from. You're taking from a population that's already normally distributed. So think about this. Even if your sample size was 1, even if you were just randomly taking people, if you randomly take people from a normal distribution, they will just start to form a normal distribution. You're just going to see the distribution of the people. So it doesn't matter that our sample size is small, because we absolutely are assured that we're pulling from a population that falls in a normal distribution. So we can assume that this will be a normal sampling distribution because the population is normal. So assuming that, we need to know, what number do we expect? We expect 30. So our sampling distribution will have a mean of 30. And the standard deviation, since we're calculating a mean, is going to be this formula here. So it's going to be the standard deviation of these crash forces is 1.5. And we're going to divide that by the square root of the sample size. So divided by the square root of 4. So it's 1.5 divided by 2. So it's 0.75. So if we take samples of 4 cars, we should expect our samples to have an average, to be normally distributed, average of 30, a standard deviation of 0.75. And I believe that the question asks specifically about 30.75. So that is 1 standard deviation above the mean. What's the probability it exceeds that level? So if we go plus or minus 1 standard deviation, this is like very similar to the last one. It's 68% in the middle here. That leaves 32, which is split evenly, 16 and 16. So we are just talking about this chunk here. The probability in a normal distribution that you are greater than 1 standard deviation above the mean, that has a probability of 0.16 or 16%. So I'm going to go with B on that one. All right, last one. Let's rock. All right, the dot plots below show an approximation to the sampling distribution for 3 different estimators of the same population parameter. So with A, B, and C, we're trying to take samples that are leading us, like, we're trying to take small samples to represent the population, to figure out what the real average is in a population. So it looks like, let's read what the question asks. So if the actual value of the population parameter is 5, so what we're trying to get with our samples is 5, which dot plot displays the estimator with both low bias, low variability? So let's think of A, B, and C. So the red dots, the purple dots, and the blue dots. If the number we're trying to get is 5, statistic C is doing a terrible job because it's giving us the number 2, or like slightly over 2. So if we're talking low bias, C is doing it all wrong. Bias, so if we look at A and B, what's the number we're trying to get? I can even draw a straight line. We're trying to get, oh my gosh, let's do that with such a different color. Okay, we'll make the line like that. So like here's where we're trying to get. But both of these do a pretty good job. They're balanced on both sides. They're pretty balanced on both sides. So I'd say both of them have low bias in the sense that they center, they start to peak. They're, oops, that's not right. But I could have even drawn that. They peak, oh my gosh. They kind of have this like peak, and it's balanced around where the center should be, 5. Which one has the low variability? So to me, it looks like the purple has a bit of higher variability from sample to sample. So I think A is going to be our answer here. It's consistently getting us around the number 5, and there's less variability than statistic B. So I think A is going to be our answer here, low bias, low variability. All right, so hopefully this helped you. Have fun, enjoy this, and that's it. Adios.